Okay, can you see my screen?
Yes.
Yes.
And can you see it in full mode now?
Yes.
Cool. Okay, so I will start. And I don't know, Walter, if for any reason I lost connection, maybe you can call me on my phone or something like that.
Yes.
Because I cannot see any camera around. Okay, so good morning, everyone. Thank you, everybody, for joining me here today. And I especially would like to thank my advisors, Walter, Rodrigo, and Fabrice, and also the jury members for being here. So the presentation today will have this structure. Firstly, I'll have an introduction section, then the part one of the thesis about the Amazon floods. Then we upscale our analysis to the large South American wetlands, which is the part two of the thesis. Then the part three about how humans interact with these water systems. And then we finish with a conclusion section. So I'd like to invite you all to join me today in a journey across South America. And we'll start in the 16th century when many European explorers came to the continent and looked for the legendary El Dorado city, the city of gold, which location was unknown and it is still unknown if ever existed. So here you can see in this map, a map of the South American wetlands, and all these parts here, these gold medals, are the potential locations of El Dorado. And indeed, they look very much to be located around wetlands. And actually, that is what these explorers found. They found marvelous wetlands instead of the El Dorado. These wetlands full of a unique biodiversity and, of course, very often these golden landscapes. And although these wetlands can be considered remote by some people, and indeed they are relatively remote, they definitely are not uninhabited. And it's not a coincidence that when we look at the map of South American wetlands here, it resembles very much the map of the Jesuit missions across South America. And actually much before the Europeans arrived here, millions of people lived in South America. Millions of indigenous people lived along wetlands, especially in the Amazon, where we estimate to have around 10 million people living along river floodplains. And these societies have largely altered the landscapes and interacted with the flooded landscapes. And today we still have the situation with many urban areas and major cities lying along river floodplains. And these human societies have had to adapt to the flood regime, as seen, for instance, by this beautiful annual indigenous calendar from the Upper Negro River Basin, where they depict in this calendar how the agriculture and all their activities and habits occur during the year and follow the hydrological cycle. And not only they have to adapt to the flood regime, but also humans alter the flood regime through river engineering approaches as building of levees and dams. In other words, wetlands should be seen as human water systems, a two-way coupled process where both humans and wetlands interact directly. And of course, not only they need to adapt to the flood regime, but they need to adapt to a changing flood regime, to the many changes in the environment due to factors as climate change, building of reservoirs, and so many other aspects. And this is a great example of the recent 2021 flood in the Central Amazon, the largest ever recorded in the region. And here you can see all these marombas, walkways, which were built along the flooded streets of the Manacapuru city. And of course, not only humans, but the whole nature adapts to the flood regime. This picture shows a jaguar in the Mamirawa Reserve in Central Amazon floodplains, where recently it was described how they evolved and how they adapted to this aquatic existence. And not only the jaguars that live many months on the top of the trees need to adapt to that, but also the trees and the vegetation itself. So here, this kind of tree can cope with up to 6 months a year of flooding. And here it comes to the definition of wetlands, which are areas in the interface between aquatic and terrestrial environments that are permanently or periodically inundated and where communities are adapted to the local dynamics. And South America has been called the fluvial continent because of its large river drainage systems, and wetlands cover a large part of the continent, up to 15% of it. And these wetlands vary in types, can be wetlands along rivers, what we call the floodplains, but also interfluvial areas that are more rain-fed or associated to local runoff processes. Here you can see in black the main wetlands, the black circles, the main wetlands we are going to study today and look at today. And in orange circles, all the Ramsar sites in South America, more than 100, which relates to these wetlands of international importance. And if you have, on one hand, the natural wetlands, we also had many cities and urban areas along these floodplains, which have been facing intensifying flood risk in the last decades. And what we know is that we have many wetlands, and they are connected in one only continent, and they are definitely not static. Actually, they pulse like a heart, as we can see in this animation, which I made based on the MGB hydrological model for South America, and where we can see the dynamic across time, space and time of inundation in many wetlands across the continent. And as I said, these wetlands are connected, and there are many ways they are connected. For instance, through birds and wildlife that migrate. For instance, this wood stork here is a species that is known to migrate between the Pantanal and the south of South America. This one, for instance, I photographed very close to Porto Alegre, our city here, and they form this La Plata-Rio Grande do Sul corridor, which connects many wetlands through bird migration. Also, we have important climate teleconnections and climate circulation processes that connect these areas, not only at continental scale, but also at global scale. So, for instance, El Niño patterns that can affect many wetlands at the same time with similar hydroclimate processes. Also, we have an important political way of connectivity. So, for instance, national scale policies are developed for the wetlands of a specific country, so that they respond to how they are located within this political context. So here we have recent inventories of wetlands that were built for countries in South America, for instance. And how to study wetlands from a continental perspective, and especially the hydrology of wetlands. So for this, we can be based upon recent advances in what has been called the continental hydrology discipline, that has been largely promoted in the last decade, and make us understand water resources at a continental scale. And in this sense, we could think of a continental scale research agenda for wetlands hydrology, which is the main topic of this thesis. And such an agenda would aim at understanding the interaction between wetlands and regional and continental climate, understanding past hydroclimatic events that affect different wetlands, understand processes through comparative hydrology approaches, assisting the development of inventories of wetlands, assessing us to understand the vulnerability of wetlands to human threats at very large domains, also to help us understanding how current observation systems across the continent help us monitoring these systems. And finally, also helping us to understand how flood hazard develops at large domains. And these are the main objectives of the thesis, which is located in this context. So basically, the main objective is to foster the comprehension of wetland hydrological process in South America from a cross-scale perspective and through a comparative hydrology approach, aiming to move forward a continental wetland research agenda capable of differentiating inundation processes occurring in large wetlands from those occurring in the widespread floodplains where millions of people live across the continent. And two main concepts I think is important here. Firstly is the idea of a cross-scale perspective, where we have this challenge of making continental analysis locally meaningful for multiple stakeholders. and also a comparative hydrology approach, where we try to understand processes through similarities and dissimilarities. And how the thesis is structured. So starting with South America continent, the first stop will be at the Amazon basin, where we study the Amazon floods from multiple perspectives. For the part 2, as I said, we upscaled the analysis to the large South American wetlands, so we will study 12 large wetland complexes in the continent. And the third part will move more to the southeast of the continent, where we study wetlands as human water systems, and especially in river basins that were largely altered by humans. And as available tools, I'll go very quickly on it now, because we'll talk more about it in the rest of the presentation. So we could say that we have 3 main types of tools. Firstly, of course, in situ data, which are fundamental for any analysis in hydrology. So we have in situ measurements of river water levels, discharges, precipitation, other climate variables. Remote sensing is fundamental, and the fruitful satellite era has provided us many fundamental data sets on variables as precipitation, water levels, flood extent, and so on. And also mathematical modeling, especially here the process-based hydrologic and hydrodynamic models that help us understanding processes in these areas. And especially here, we talk about 1D and 2D hydrodynamic models. We can understand the 1D as simpler hydrodynamic models that simulate wetlands as relatively simple storage units along rivers, while 2D models are more complex ones that can simulate the 2D flow patterns that occur across wetland systems. So moving to the thesis part 1, which is called the Amazon Floods, Wetland Types, Extent and Trends, and is composed of 3 chapters. So the Amazon River Basin, the land of superlatives, where many different and interesting wetlands exist. And these wetlands vary from the floodable savannas here in the south, in the Madeira River Basin, the Llanos de Mocho region, up to the Roraima savannas, to the Negro ones, and also to the still poorly known peatlands of the Pacaya Samiria in the Peruvian Amazon, and to the main floodplains along the Amazon River. And the main focus of the first part will be the Negro River Basin, where we try to understand different wetland types that exist there. So from a hydrological point of view, we could think of 2 main types of wetlands, which can be an interesting approach, which is differentiating between river floodplains that are located along rivers and are mainly fed by overbanking flow and waters from the main river. And the other type is interfluvial areas, which are less connected to the main rivers. And in the case of the Negro River Basin, are associated with neotectonic processes that created regional depressions in the terrain, and this ultimately led to a very different vegetation and soil type in these areas in contrast to the adjacent forests. And to understand how occurs the floods and what is the flood dynamics in these complex wetlands, for this chapter we employed 1D and 2D hydrodynamic models. So we developed and applied these models, and we validated them with water level from satellite altimetry data over rivers and wetlands. And what was clearly from the beginning, so here you can see the time series of water level for river floodplain and for an interfluvial area. And in black is the 2D model, in red the 1D model, and in blue the satellite data. So it's very clear that in floodplains there is a very large water level amplitude across the year, while in interfluvial wetlands it's much smaller, of less than 1 meter the amplitude. And what we saw later is that the 1D and the 2D models are capable of simulating the river floodplain dynamics, but only the 2D model is capable of simulating this small water level amplitude. And this, together with other reasons, made us understand that 2D models are indeed preferable over this interfluvial, but not over the floodplains. And when we look at the flood extent, so here we have the maximum flood extent maps based on remote sensing and based on models for this basin, the Negro River Basin. And here are the time series of flooding based on all the products that we had. We see very clearly that there are some convergence among the products, but still there are a lot of divergence. And the optimal solution to understand what's the actual flood extent in the basin should be a combination of both remote sensing and modeling approaches. And this led us, motivated us and led us to the next chapter, which tries to understand how much inundation occurs in the Amazon. And this was motivated also by the understanding that there are today many inundation datasets available to map inundation across the basin, but a comprehensive assessment of these datasets is definitely lacking. And for that, we performed an extensive data collection, collecting up to 30 datasets, covering a large domain of spatial and temporal resolutions. We collected data for local wetlands, for individual floodplains, but also for the whole basin. So there are many products available for the whole basin. And then we compare them. And the first point was to plot the annual maximum and minimum inundation. So here you can see the time series. So each line corresponds in dashed lines the maximum inundation, and the continued lines is the minimum inundation for each dataset. And here is flooded areas, here is the time series. And basically what we see is a complete mess, right? It's very complicated to understand what's happening. And indeed, this shows very clearly that we have a very low consensus among the datasets. And we need to understand why are they so different. And but if you look here, you can see that the annual maximum inundation can go from 900,000 square kilometers for some products up to 100. So it's very large, the discrepancy. And we need to understand why each product is showing that. If you look at the long-term inundation, maximum inundated area, based on all data sets, we have this figure of almost 500,000 square kilometers, but a very large uncertainty. And if we look on the synthetic aperture radar, the SAR data only, which are supposed to be the more, the one that you can trust more, then the estimate goes up to 600,000 square kilometers and the uncertainties decrease. But based on the local products and the analysis we did, we estimated a basin scale underestimation by SAR data of around 10%. And trying to understand, to move further and understand the spatial agreement among the data sets, we created this map where for each pixel, we counted the number of products that agree that that pixel is flooded for the maximum inundation extent. And so the more blue here, more agreement we have that this pixel is flooded. And when we look at this map, we see that we have a higher agreement here in these parts, and this is the lower Amazon floodplains associated with more open water areas and big lakes. Then an intermediate...
Ayan, excuse me one moment. Does everybody see the slides advancing? I'm stuck on the 11th.
Yeah,
the 11th
I'm stuck on the same one.
Ah, now we're moving. Okay. This. Okay. Perfect.
Yes, I have the same problem.
Okay. I'll just connect the internet cable here. Just a second. Let's see if it improves. Okay, now should be better. Do you see it?
Yeah. Now we can see the agreement among data sets.
Okay, good. So I'll talk again about it. So basically, each pixel here shows the agreement among the data sets, and the more blue colors indicates the higher agreement. So we can see this very high agreement along the open water areas in the lower Amazon reaches, and then an intermediate agreement over for these forested floodplains here, still along the floodplains, and the lower agreement in the floodable savannas, where the flooding dynamics is indeed more difficult to predict because it's more erratic in space and time. And also, we created a user-friendly WebGIS for visualization and downloading of the dataset, so you can check it in this link here. And while analyzing this data, we realized that you had a great opportunity here to not only look at the spatial agreements of where inundation and how much inundation occurs in the Amazon, but also to look at the temporal variation of this inundation. And this was especially motivated, and this is the last chapter of part 1, this was especially motivated by this very, very big flood that you had in the basin in June of 2021. And what is known in the literature is that, and is well described, is that there is a very clear pattern of increasing precipitation and increased water levels along the central Amazon and increased precipitation along the northern part of the Amazon basin. So here in this map, all the blue points show a positive increase over the last decades of precipitation. So we can see this northern part of the basin with an increased precipitation. And this has translated into an increase of water levels across Central Amazon. So here you can see the trends of water levels, and which culminated with the largest water level recorded in Manaus this year. And what we thought, based on the data sets that we collected before, is that we had the opportunity here to understand how this increase in precipitation and water levels have translated into inundation extent. And for that, we leveraged 3 data sets that cover the 4 decades and that cover the whole basin. So these are the data sets. And we plotted the trends. And when we plotted the trends, here we have the Amazon basin. So each pixel here, if it's blue, is a positive trend in inundation between the 1980s and 2020. And basically we see that the main parts of the Amazon basin that have an increasing trend in inundation is indeed the central Amazon. And if we plot the time series of the inundation anomaly for this Amazon central region, the central Amazon region, we see this time series and we see clearly that it has increased. And when we quantify it, we showed that this increase was of about 20% in the maximum inundation extent along the last 4 decades. This is a very expressive and large value. And not only the maximum inundation extent has increased, but also the annual amplitude of inundation. The flood duration has increased in around 70% in this, especially in these open water areas here that we were able to build the analysis with more confidence. And also the surface water connectivity has increased, which has a lot of importance for ecosystem management and understanding. So based on this understanding of the Amazon basin, it's missing, but now I had a slide for the part 2. So based on the understanding of the Amazon basin, we moved to the part 2, where we try to upscale our analysis to the main South American wetlands. And it was a natural continuation of the study, since we were studying many individual wetlands that occur in the Amazon basin, the Negro savannas, the Llanos del Mocho savannas, the central Amazon floodplains, and then we wanted to see, okay, and what about the other wetlands in South America? And this is what led to this new chapter, the new part 2. So basically, we selected 12 large wetland complexes in the continent, which vary in latitude, vegetation type, soil type, climate, and it covers from the continent from north to south. And to study these wetlands, we performed a comparative hydrology approach, where we compared hydrological variables of precipitation, of inundation, of evapotranspiration, and water level. So we collected this data for all these wetlands, all of them based on remote sensing products, and try to understand how the wetlands differ in terms of hydrological processes. And so this part has 2 chapters, and the first chapter is the chapter 7 of the thesis, which is called South American Wetlands from Space, and where we study the flood dynamics of wetlands. And so when we look at the 12 wetlands and we look for the largest maximum inundation, this is what we get. These 3 here are the largest wetlands in terms of maximum inundation. in the continent, and they have each around 100,000 square kilometers of flooding every year. So it's the Amazon floodplain, the central Amazon floodplain, the Llanos de Mochos region in the Upper Madeira, and the Pantanal in the border between Brazil and Bolivia and Paraguay. So this 100,000 square kilometers is a very, very large flooded area. It's perhaps half of the Rio Grande do Sul state area, so it's a very large area. And one important thing to understand here is how flood propagates along these wetlands. And recall that from the Negro River Basin analysis, we had these categories of floodplain and interfluvial wetlands. So if you look at the Pantanal, which is the main Pantanal area, is mainly a floodplain area, and the Llanos del Orinoco is a main interfluvial area with less connected savannas to the main river. So if we plot here in this map of the Pantanal, the month of maximum precipitation for each pixel, we see that most of the region, the precipitation peaks at January. And the Orinoco is in June and July, right? But when we look at the month of maximum flooding, so again, each pixel has the month where the maximum flooding occurs, we see that there is an upstream to downstream propagation of the flood, so that the upper areas have a peak of flooding in March, and the most downstream have a peak in July. This means that there is a very long and slow propagation of the flooding across the area. While in the interfluvial area is the opposite, because in the interfluvial areas, the processes are more vertical. We do not have this lateral propagation so expressively marked. And in this sense, the flooding occurs just 1 month after the peak of precipitation. So here is June, and the flooding is in July, and this part is in July, and the flood is in August. And when we analyze the 12 wetlands together and look for this lag between precipitation and flooding, we see that indeed the interfluvial areas have a delay of up to 2 months, and the floodplains of at least 2 months. And the Pantanal has the longest flood delay in the continent. And more than that, we can analyze the water level amplitude and compare water level amplitude across the wetlands. So here for each wetland, we have the polygon of the wetland, and each dot and square here, it's one virtual station of satellite altimetry that provides us data of water level. And we collected around 900 satellite altimetry data. It's a collection that is still going on, and we hope to have more virtual stations, especially over wetlands, in the near future. And here we plot each color referring to the water level amplitude, so that gray colors indicate a very low amplitude across the year. And this is what we see again. We saw a very similar pattern for the Negro Savanna, and here we can expand the analysis for the 12 wetlands. And we see that indeed the river floodplains have a very large amplitude, like the Amazon, the Paraná rivers, the Madalena rivers, especially the Amazon River, which can have an amplitude of more than 12 meters in some parts, while the interfluvial wetlands have a much lower amplitude of less than 2 meters. And the second and last chapter of part 2 talks about evapotranspiration and how floods in the wetlands affect evapotranspiration. And why evapotranspiration? Because this is the main variable connecting surface and atmosphere. So in terms of water, so it's a fundamental variable to understand from a regional and continental perspective if you want to understand how wetlands affect climate. And to do that, we developed a new method, a new algorithm to estimate evapotranspiration in wetlands based on the GSEBAL algorithm. You can check the publication here. And our results you can also check in this WebGIS in this link here. We uploaded our results there. And I think that the main result here is when we compare the wetland with the adjacent upland to understand what are the differences in evapotranspiration. So in this figure, you can see, so each dot refers to the wetland, and the connected square refers to the adjacent upland. So each pair here is from wetlands. You have the Pampas, the Paraná, the Chaco, the Pantanal, and so on. And the color refers to the climate. So the green colors are the temperate wetlands, while the red colors are the equatorial wetlands. And when we compare them, we see that there is a larger difference between wetland and uplands in this region, which are the temperate wetlands, and there is a smaller difference in the equatorial ones, like in the Negro and the Amazon region. And this means that temperate wetlands tend to alter the regional evapotranspiration more than the equatorial ones. And of course, it depends on many other factors as flood propagation along the terrain, the existence of a consolidated river drainage system or not, and other factors. But this is a general picture of the changes in regional scale evapotranspiration. And once again, the Pantanal, as we saw before, it has a very long propagation of flooding. So we have the upper regions where the flooding peaks in March. You can see here the annual flooding regime. So this is the upper region with the flooding peak in March. Then we move downstream, and the most downstream here in the south of Pantanal, the flooding peaks in July. And this was very interesting, is that we could see in the evapotranspiration estimates based on remote sensing data that this propagation of flooding also alters the regional evapotranspiration from the wetlands. And this can be seen here. So each line here relates to one of these regions of equal month of flood peak. So basically the most downstream regions have led to a higher evapotranspiration rate at the end of the year, while in the upper reaches it's more even, the distribution of evapotranspiration. And this has a lot of implications for regional climate understanding across the Pantanal region. Then the final part of the thesis is the part 3, where we try to understand wetlands as human water systems, and where we realize that humans alter the landscape and we need to understand how wetlands and humans interact. This is actually the main topic of social hydrology studies in the last decade, and although this is not a social hydrology thesis, it was an important concept coined by Giuliano Di Baldassarri that we wanted to bring here. So this part is formed of 3 chapters, and recall this figure from the beginning of the presentation. If you have the natural wetlands from one hand, we have these cities under intensifying flood risk and that lie along river floodplains in the continent. And this will be the focus of the last part of the thesis. So here we have a map of flood vulnerability in Brazil. Unfortunately, it's not for the whole continent, but it already provides us some good understanding of how important is the flood risk, especially over the coastal areas of Brazil, where most of the people are located, but also along the main wetlands, the large rivers, in the Amazon basin, the Pantanal, and so on. We have some important flood vulnerability degree. And as I said, we have 3 chapters in this part. The first chapter, chapter 9, is about the great 1983 year in South America, which is perhaps the most devastating year in terms of flooding in the records of the continent. And this year led to hundreds of thousands of people being affected by it in multiple aspects, economical and even human losses. And to understand it, we applied the idea of continental hydrological modeling. So here you can see some, in this slide, I showed some pictures of the União da Vitória in Paraná for the July 83 big flood. So to understand the dynamics of the 83 floods, we applied and assessed the MGB, Continental Scale Hydrological Model, developed by Siqueira and collaborators, for extreme discharges. So in this animation here, we see in the left the daily precipitation dynamics for the whole continent. So each day you have the precipitation field. And here on the right, we see the dynamics of daily discharges across the continent. So we can see the more red here is the more affected river reaches for a given day. So for instance, now we are approaching June and we see the floods here in the Paraná. Then in July, the floods move southward. And by looking at this map, we summarized this animation and these model outputs with this figure here. So basically in the left, we have the return period for each river ridge. So the more red the ridge, the more extreme was the 83 flood in this particular ridge. And in the right, we plot the month of peak discharge. So here you can see in red the ridges where the flood occurred in January and more in blue in December. So it's very clear that there is a southward direction of the month of peak discharge. And what does it mean? It means that different floods occurred throughout the year. So it was not one big 83 flood, it was many, many different floods. And this was a very strong El Nino year. And this led to this, was the main factor explaining the extreme precipitation that you had. And in summary, we had the largest floods ever registered in many parts of the continent that occurred in many different months. And if we assessed here that river discharges are well represented by the model, so we validated the model with in situ data. Here, for instance, you can see the river ridges, the lines refer to the model and the circles refer to the in situ data, so they have a very good convergence and coherence. So if the models can represent well the discharges, what about other variables, other important variables such as flood extent and water levels? And this leads to the second chapter of part 3, the chapter 10, where we try to understand whether these continental models can be considered locally relevant in terms of variables different than river discharge. To do that, we employed a hydrological model, the MGB model, at 3 different scales. And we applied it to the Itajaí basin, which is a basin here in south of Brazil, and which has a lot of in situ data available, so that it was a very good case study for us. And it's a very important basin in terms of flooding events in the continent. So basically we applied the MGB model at 3 different scales, a global approach with some coarser input data, coarser resolution, coarser DM, coarser spatial resolution, and coarser cross-section data. And we applied also it in a regional approach with more detailed data, and then a local approach with very detailed data that we had access to. And we compared the 3 approaches, the global, the regional, and the local, with a benchmark, which was a very detailed HEC-RAS hydraulic model that we developed for the basin with more than 600 cross-sections. And when we compared the different model setups, so we have these results. So here we have the flood extent data. So we have the reference, the HEC-RAS, which is we assume as the truth. We have the continental, the regional, and the local model setups for flood extent. And it's very clear that the continental has a coarse resolution in comparison to the reference, while the local model setup resembles much more the reference. And when we look at the water level simulations, we have a similar result. So here we have the water level profile across the river longitudinally, and the light blue here is the global model setup. And if you see here, the dark blue is the reference, the HEC-RAS simulation. And the REC-RAS is much closer to the local model setup, the red one. And the question then was, we saw that the local model was closer to the reference, but could we assume it as locally relevant? And for that, we proposed some criteria. I won't enter into details here for brevity, but we proposed this criteria based on performance metrics, as Nash-Sutcliffe and root mean square error metrics. And what we concluded is that indeed the continental models can provide locally relevant discharges, as we saw in the previous chapter, but on the other hand, it cannot provide locally relevant water levels and flood extent. And this shows that current models still need to have a lot of room to develop and to improve in the near future. And indeed, there are great opportunities to do that. The forthcoming satellite missions oriented to hydrology will provide many important data sets that will help us improving these models. So this was the conclusion related to current model capabilities. And then the last chapter of part 3 talks about the river floodplain reservoir continuum. And this was very clear for us that it was an important way forward to consider when we realize that not only we need to improve the models in terms of resolution and input data, but we need to improve the representation of processes. And in human-altered basins, where we have many, many reservoirs, as is the case of so many basins in South America, we need to consider this human alteration in the context of the river floodplain interactions. So here we have, for instance, the Itaipu Dam, the big Itaipu Dam in the Paraná River Basin, and the Parque Nacional da Ilha Grande, which is a very large and ecologically relevant floodplain just upstream from the dam. And we need to understand how this continuum of processes occur across the basin. So for instance, if you look at the Iguaçu River Basin in the Paraná Basin, here we have the water levels simulated by the models, and we have a whole dam cascade. So we have many dams along the river, but also have rapids, we have the Iguaçu Falls, we have important floodplains. And the big question here is that we need to have a tightly coupled integrated model that is able of simulating all these integrated processes. So we did it, we created this model and we applied it to the Paraná River Basin. We had some success on the simulations and the approaches, and especially with the validation of the model. And then we used that to understand how floodplains and reservoirs affect floods across the basin. And this is the map. So basically the colors indicate how much attenuation that process affects the floods. So basically here, when you look at the floodplain effects, we see for the basin that it has a lot of important effects on the upper reaches and along the very lower reaches. And the reservoirs have a main effect along the main tributaries. In other words, they have a complementary role. Floodplains and reservoirs have a complementary role on attenuating floods across the basin. And so to conclude the thesis, I hope you have enjoyed this journey across South American wetlands. I provided my view and a cross-scale perspective and a comparative hydrology approach for these wetlands. We address different wetland types, different hydrological variables. We try to understand wetlands as human water systems which live where humans live within floodable environments and alter the landscape. And indeed, there are great opportunities for continuing this research agenda in the near future. The satellite era, the advances in continental scale hydrological modeling, which should be more tightly integrated towards locally relevant predictions and towards what I understand a seamless understanding of surface water dynamics in the continent, where you can have a thorough understanding of the spatial temporal dynamics of rivers, wetlands, lakes, reservoirs, all together in a seamless way. So after all, at multiple scales, the South American floods reveal the fascinating world of a seamlessly connected nature. So to conclude, I'd like to thank all the collaborators that I worked with during the last 4 years, especially my advisors, and all those researchers that I had a great pleasure to interact and without whom this thesis would not be possible, and especially my colleagues from the HGR research group. And also I understand that a PhD goes much beyond the thesis document itself. So I was very happy to be involved with many other researchers in the creation of the Conexões Amazônicas network, a network for science, for promotion of science communication in the Amazon. So you can check our activities in this website. And also I had the pleasure to do my research not only on the computer, but also I had the opportunity to visit and to study in loco many of these wetland systems in South America during the last four and more years, actually. So I really encourage everybody to do your research not only on the computer, especially for the Earth system community. And that's it. Thank you very much.